today we're going to talk about vector semantics, and this is a way of trying to represent the meaning of words by a vector of numbers. It's often called word embedding, and it's become more fashionable over the last 5 years, let's say. But we've been doing things like this for a long time in natural language processing. And we're going to talk about both the theoretical underpinnings of what's going on and why we're doing it, and some of the newer techniques that allow us to be able to represent the meaning of a word by a bunch of random floating point numbers. They're not random, but they may as well be. They're not going to be obvious if you actually look at them. You're probably already aware, based on your projects, that when you're trying to look at two words and try to decide whether they're the same or not, sometimes they are the same, but they're not exactly the same bunch of letters that are in them. And so what you get is slight modification, or maybe slight meaning differences that you really like to care about. Okay? So for example, if we have the words fast and rapid, they sort of mean the same thing. But if you're just doing a letter by letter distance metric, these words are completely different. And so fast and slow are as different as fast and rapid. And that doesn't seem right. Okay? You'd like, in some sense, fast and rapid to be closer together, so the distance between them is not as big as the difference between fast and slow, because they're opposites of each other. Okay? And same way with tall and height, especially if you're trying to do some sort of find an appropriate sentence within a Wikipedia article that might answer a question. You'd like something to be not penalized if it talks about the height of the thing when you're looking for how tall it is, because these are related words. They're talking about the same context. There's no overlap. There's no reason for these words to be treated the same. Historically, they've come from different languages, but they mean something similar. And so we like something that, rather being just a 0-1 distance between words, is some sort of distance between words. Okay? So that's the underlying thing that we're trying to get out of this. Okay? We do this for lots of NLP tasks where, say, detecting plagiarism, we'd like to be able to say, these are the same things, even though some words are different because the structure's the same. We'd like to be able to do this in recommending alternative ways of saying things, which is almost the opposite of plagiarism. So you want to be able to get information, but also question answering. You want things that have not just this extreme 0-1 distance. We'd like it to be a little bit more lenient in the distance between these things. One of the other things that we've done in this space in NLP is look at how words have changed their meaning over time. Okay? Words don't have a static meaning, and depending on their context, they actually change over time. And old people like me get annoyed about it when you use some word that's got a different meaning than what. When you talk about AI, okay, whatever that is, and old people like me have a different view of what AI is, but the point is that artificial intelligence has changed its meaning over the last 30, 40, 50 years. So this one on the left, I always like this one because it taught me something when I saw it, and I thought I knew things about older English. So if you look at the use of the word dog, the use of the word deer, and of the word hound over the last 800 years plus, and look at the words that appear in their context, what you discover is that pre-1200, the word deer, okay, that we now think is some relatively large animal with antlers that people shoot, whether that be Bambi's mother or they're shooting in deer hunting season. The word deer actually in English used to just mean big animal in the forest, which included things like dogs and wolves and hounds. Okay? And so that's a little bit, if any of you know German, you'll know that Tiergarten means zoo. And Tier is really the word deer. It's the same cognate. So it just means animal garden. And so there is some historical aspect of that is still there. But if you look at the use of the word deer, you notice that actually it means can include dogs as well. Likewise, historical changes. If you look at the word gay, over the last 150 years, it's also changed its meaning. The word gay in the 19th century really meant happy, okay? and now it means homosexual, possibly male homosexual, but it might not be gendered. But gay has changed its meaning, okay? And this is normal in language, that language changes the meaning. Some of these things are very obviously different, but some of them are much more subtle about what the meanings of these are. And we'd like to be able to understand what these are because we learn something about how things, and we might also misinterpret things that were written 50 years ago because the language was different, okay? So how can we find similarity between words? Well, there's this thing called the thesaurus. The thesaurus is a collection of words looking at the similarity in meaning. But one of the big problems of them that they don't exist for every language, they don't exist for every domain, they don't exist for every year because we can change the meanings of words as we're going through our lives, and also depending on the particular domain, the particular community that we're in, words can have different meanings, and we'd like to be able to get that and discover it automatically. Okay? Now, Selicanis, a linguist in 1954, said oculist and eye doctor occur in almost the same environment. So if you look at those words in American English, because I don't think oculist appears in British English, but if you look at these words and look at the content, the context that they appear in, you'll discover it's very, very similar. Okay? And rather famously, another linguist in 1957 first said, you shall know a word by the company it keeps. With the idea that if you look at the contexts of words, okay, you find that the words that have similar meaning have similar context. So the words round about them sort of define what the meaning of a word is. Okay? And we do this when we're trying to interpret things. So here's a short example here. We have a bottle of Tisquino is on the table. Everybody loves Tisquino. Tisquino makes you drunk. We make Tisquino out of corn. Now, hands up if you knew the word Tisquino before I showed it on the screen. I should use that rather than Nebuchadnezzar. Okay? But what do you think Tisquino means? It probably says somewhere. It always does say afterwards. So you're going to say alcoholic beverage like beer. I must admit, I don't think this is immediately clear of whether it's a spirit or whether it's a beer, whether it's actually distilled or not distilled. He says, my distinction between these things.
That's just like normal, like grain whiskey, right?
I thought it might be that, although rather interestingly it says alcoholic beverage like beer, but maybe somebody made this slide thinking that, oh, this is America and we're not supposed to talk about spirits.
But yeah, also the word corn used to just mean like any arbitrary grain. This
Right.
was like that in the 1600s
Yes.
when maize was American and it was grown there.
Yes.
Maize.
So again, these words, but you get the idea. So in other words, reading this to me, I think, but it's probably whiskey-like, okay? But it's because I don't recognize it, although I recognize the ending of it as being a probably Portuguese ending. It's a diminutive in Portuguese. So I think, well, it's South America, so it's going to be tequila rather than whiskey. Although the difference is, not major, apart from one's made in Scotland and the other ones are not. But you can work out what that meaning of that word is, having never seen it before, and you have a fairly good idea of what it means, okay? And you do that because of the context, because if you replace it with the word whiskey, okay, it's almost right apart from the corn bit, okay? But, as you say, it's some sort of grain, okay? And so that's telling us something about similarity between words if they appear in a particular context, okay? So we can try to represent that computationally, okay? And we can do that, and we're going to talk about this in three distinct ways. The first one is mutual information weighted word co-occurrence matrices. So we're going to say what words actually are used in the context of this word, and we're going to use that to talk about the similarity between words. The second way is trying to reduce that. Instead of having this big long vector where our vocabulary of our words will have lots of zeros in it and the occasional one, we could try to reduce that into a reduced dimensional form using standard mathematical statistical techniques. Okay, so that's number two, singular value decomposition or some sort of PCA, latent semantic analysis. We're going to talk about three which is a neural network inspired method to try to do something similar, to try and get a more reduced, dense representation. And we're going to talk finally about brown clusters, which is best described as another technique, because it's sort of different and interesting. So we'll actually talk about it. What we're really interested here in finding these embeddings, we're really interested in getting something whose distance metric between them captures that fast and rapid is close and fast and slow is not close. Okay? So we're going to talk about vector semantics. We're going to first talk about words and co-occurrence vectors. Okay? We can represent in a document how often a particular word occurs. Okay? So what we could do is we could say, okay, for a particular document, we could just count up the number of words. Okay, just count up the number of words, the number of times it occurs. So, for example, we take 4 plays from Shakespeare. Okay, good examples of modern English. It's not modern English at all, but let's pretend it is. We take battle, soldier, fool, and clown. All of these words appear. And what we do for each of these different plays, we look at the number of occurrences. So in As You Like It, okay, which is a comedy, we find that battle appears once, soldier appears 2 times, fool appears 37 times, and clown appears 6. If we look at 12th Night, also a comedy, we have 1 to 58 and 117. Well, we look at Julius Caesar and Henry V, both of which are not called battles or action movies as they would be called now. They're called tragedies, but they would be action movies if they were made nowadays. We discovered that battle and soldier are much more common in those compared to fool and clown. Okay, and this tells us something about both the plays with respect to these words, but also tells us something about these words in the fact that which of these words are more similar. Okay. So what we could say is the 2 documents are similar, the vectors are similar. Okay? So in other words, if their distributional properties are similar, so we say that Julius Caesar and Henry V are more similar plays to each other than As You Like It and 12th Night, because Julius Caesar have got battle and soldier as being more common and correlated than fool and clown. Okay? So we can actually do this to look at whether the documents are similar, or we can look at whether the words are similar. So if the words appear in over a number of documents about the same number of times, we can say these words are somewhat similar. So in other words, fool and clown, okay, are more similar to each other than battle and soldier are more similar to each other, and these are separating out. So we can use the multiple plays to try to make decisions about whether these are similar words. Okay. Now, instead of using the whole document, we can actually use the paragraph. Instead of using the paragraph, we can sort of use the little bit of context and say 4 words either side. It might be 3 words either side, but some limited form of that we could actually try to work out what the similar form is. So in other words, what we could say is we could represent a word. Every time we get a word, we could look at the words that appear round about it, 4 before and 4 after, and then try to classify, okay, what the word is like based on the context that it's actually in. Okay. So here's another example where we're looking at this with respect to Apple, Pineapple, Computer, and information. Okay, sorry, not Apple, apricot, because Apple would be confusable with computers. And what we find is that there are certain words that appear next to apricot and pineapple, particularly pinch and sugar. Okay, while digital and information, you're more likely to find words like computer, data, and result. So we have a difference between there based on the number of occurrences of words that appear in context. Okay? So we could actually try to build that as a representation for each of our words. So instead of saying words are just going to be the word, we could actually say what's its most common words that appear in the context of this word, and we could use that as a representation of the word, and then start talking about distance metrics in that domain. Okay? Now, if you do this, it works. In fact, that's what we actually do often for trying to get representations. And what we discover is if we use local context, 1 to 3 words, we get quite a syntactic representation, so we find that the similar nouns go together. If we do longer context, what we discover is we get a little bit more semantic context, because we're picking up the verbs and things that are in the context. So as you make that bigger, now it's hard to make the decision about what you should do, because you don't know how much context you should take into account, and depending on the data that you're training from, you're going to get different quality of results, and that's what we're going to go in and actually talk about. Okay, so one of the things we could do, okay, is we could look at the first order co-occurrence. So what we could do is we could say, well, what is the, let's make sure that I get this right, because I always get confused. The words that are typically nearby, so wrote is a first order co-occurrence with poem, because you're likely to get the word poem or book near the word wrote, okay, because poem is something that would be an argument to wrote, okay, while the other one is, we could say, the second order is not saying about X being near Y, but what other words are near Y, what other words appear near book or poem, and we might find that words like wrote and remarked are nearby, because the arguments that go with wrote and remark, say opinion, are actually more likely. Okay, so we can talk about what the relationship is, or what the contexts are similar. Okay, we can actually get a slightly better measure for this rather than just doing counts. The problem of doing counts is there are frequency of words are much more common, and therefore that's going to skew the output. And not only are the much more common words like the and of, but also within the particular document you might actually find things are different. When we looked at the fool and clown, the numbers were much bigger than the numbers for battle and whatever the other one was, soldier. But even though there was sort of equal distinction between those, the magnitudes of the numbers are different. So instead of that, what we could do is actually try to normalize that out, okay? And we can try to do that with a thing called positive pointwise mutual information, PPMI, okay? Often we just call it PMI, and we don't talk about the positive thing because it's always positive, and I'll explain why we want to care about that, okay? So here's a formula for it. Okay, well, here's the formula for pointwise mutual information. And really what we're trying to do is look at the ratio between the joint probability and the independent probability. That's all we're doing, okay? And so are these things more likely to be together by chance, or less likely to be together by chance, okay? So we can talk about the pointwise mutual information between two words. Oops, sorry, that's completely unreadable, because it's not doing the display properly, because there's two slides there at the same time. Sorry, you're going to have to work that out. So we're trying to work out that what that is, and I'm going to talk, and so we can actually explicitly work this out. There's a bunch of math here. It's pretty obvious. We're just going to look at what the occurrence of these are. We're going to work out what the probabilities and what the joint probability is, and calculate what the values actually are. And we've calculated what the values actually are. And here we get the pointwise, positive pointwise usually information. So we get numbers, and these numbers are effectively normalized out the frequency of things. The reason we care about the positive one is a little bit weird, and that is once we get negative, things are very different, okay? And we as humans sort of don't care about, we care about when things are similar and when they're not similar, but we don't really care about the amount of non-similarness. Okay, so for example, let me say something like, we're probably going to all agree that fast and rapid are close together, okay, and fast and slow are far apart, okay, but fast and Nebuchadnezzar are separate. But what about Nebuchadnezzar and that alcohol drink that we mentioned, which was called Tesrino, okay? It's like, so are Nebuchadnezzar and Tesrino closer or further apart than Table and Berlin? Okay? It's like, I don't really know. They're lower frequencies for me, but I don't know what this is. And that these would have negative pointwise mutual information, and we sort of don't care about that space, because one, it's never going to affect our algorithms, and two, humans don't have good perception of it, and actually the algorithm doesn't really do that when you get low frequency words. You don't get things. When they're similar, you get something useful, and when they're not similar, they're just off in some weird space. So we sort of don't care about it, and that's why we care about grounding it in zero. We never make it smaller than zero. Okay? So very real words can have very high PMI, and we can try to get rid of that by various techniques of doing smoothing to try to get better numbers, but this is really why we're caring about the positive ones rather than the all of them. Okay, so we can smooth the data to be able to do that. So we can talk about measuring. Once we get these vectors, we can talk about some sort of measurement between these vectors. And so what we can do is we've got a big long vector with lots of numbers in it, and we can find out whether these numbers are similar or not. We can do some simple thing about just doing distance metric. So we go along and just take the difference, the absolute difference between them. That will definitely have some notion of similarity between them. What we could do is some sort of dot product, where we basically look at all of the values and multiply them together. So we're actually going to boost things that have got common bigger terms and not take things that have got common smaller terms together. And we'd also be cancelling out ones where we have zero in one vector and a number in the other, okay? Which means there's no similarity, so we're cancelling them out. And this sort of works. It has the properties that we would sort of like. You've got to have some task that actually uses this to work out whether this is reasonable, but it works fairly well, okay? Right. The next problem is that if you're looking at two vectors and they've got different sizes, they've got more terms, you're going to get more numbers out of one than the other, so that number is going to artificially get bigger because you've added more terms to it. And so maybe you want to do some sort of normalization for that, because things that have got more terms will have bigger numbers, and you don't really want that. You'd like them to be similar. You could divide it by the number of terms that are in it, or you could find something else. What we typically do, as has been mentioned before, we do what's called cosine similarity. It's not immediately obvious why this is cosine, but it is cosine, because you think what's it got to do with trigonometry, but it does. You can look at these vectors as being angles in n-dimensional space. And if we take this formula here, okay, if we take the product of the vectors and the magnitudes divided by the magnitudes of each of the vectors, this is actually the angle between the two things in n-dimensional space, okay? This is not immediately obvious, but it is true. And this means that what you can get is a representation which actually sort of cancels out the magnitudes of these and cares about the difference between them. And this, independent of the math, is a really good measure for looking at the difference between two separate vectors. And so cosine similarity is a good idea. It's big when things are similar and small when they're not. And if you have sparse vectors, it's fine. It's a good thing to do. Actually, when you have dense vectors, it can be a reasonable thing to do as well. Okay? I'm going to skip the math because I've got lots to do in this. So we can treat them as angles, and really what we're getting is the cosine difference between them, and it helps reduce the cares less about the magnitude and the number of things that match, and so you get much more to be a difference between the vectors. And what you can do over a data set, is you can look at all of the words and the cosine similarity between all words in your data set, and you can collect the data together to find out which words are closer to each other. And so here, for some particular data set, I have some examples here, and what you see is down the bottom we've got place names, mostly countries, and a little bit further up we've got cities, actually North American cities, because Tokyo we know is in North America. There's probably a Tokyo in Ohio, because there's always somewhere in Ohio with a name. We've got a bunch of animals, and we've got some more detail here. Cat and dog are next to each other, while puppy and kitten are further away because we don't really care about cats and dogs, or maybe. Likewise, we've got parts of the body higher up, and this is automatically found from their cosine similarity using positive point-wise mutual information over a large amount of documents, almost certainly newspapers, given the slide. Maybe it says, oh, it's from 2006. So it's unlikely to be Wikipedia because it's too early for Wikipedia. There are other measures. So cosine similarity is not the only measure, and some people swear by using the other measure. Okay. Often using the other measure can be better, but usually it sort of works with one and it's better with the other. If it doesn't work with one, it usually doesn't work with the other. Okay, because the distribution is not the same. Okay, but people can use Jacquard dice or a modified form of Jacquard because sometimes it's better, and sometimes the option is there and you click on all four and find out when one is better, but you can't really justify why. But they're available, and you can do things. There could be reasons for choosing between. Okay. All of this is really looking at a somewhat localized choice of words, looking at, say, 4 bound. But maybe we could actually care a little bit about not just the context with respect to the words nearby. Maybe we could use syntax and try to get a better representation. Okay. And this comes into this whole notion of, if you think about verbs and you think about the subjects of verbs, particular verbs will have restrictions on the types of subjects and the types of objects that they take. You can still probably put anything in there, but if you take a verb like write, the sorts of things that do the writing are going to be animate objects. Well, okay, they need pencils, right? Okay, but they're not animate objects. And pens and typewriters and computers, maybe they write. Okay, but in general, it's going to be name of author. It's going to be, you know, a person who writes. And the things that get written, the objects, okay, are going to be things like books, poems, articles, opinions, answers, and not things like chair or apricots. You don't write an apricot, I think, okay? And so it would be nice if we could actually say, well, we could try to classify these verbs based on the subjects and objects that we're likely to see. And likewise, it would be quite nice to try to classify objects with respect to the verbs that they could go with them, okay? Because it tells you something about it, okay? And so that's one of the things that we'd like to be able to do. And so we could do that if we had the information about telling us what the subject of the verb was and what the object of the verb was. So instead of having previous word or previous word or up to 4 previous words and next words, what we could do for a table when we're extracting the information is say I'm going to have subject, I'm going to have object of if I'm looking at verbs, or I could have, if it's a verb, if it's an object, I could say what's the verb of this. And that might not be nearby. We know that syntax allows us to be able to put complex information and sub-information that the local information might not have that. But if we had a parse, we could actually use that information and put it in our table and then use that as a way to be able to look at our positive pointwise mutual information and then use that in our vectors to be able to get that information. Okay? And this is a good thing to do often, assuming you have enough data and assuming you have a reasonable parse to be able to do it. So we're not just going to use the local words, we're going to use grammatical relations to be able to do that.
So that parse has to come from a human?
Well, the parse has to come from somewhere. Realistically, we're not going to ask humans to parse all of Wikipedia for us, so we're going to run an automatic parser. Okay? Which will have some error in it, but it's still probably going to give you some information about it. Okay? And so, realistically, we're going to run a dependency parser because it gives us information almost directly over the data, and we're going to look at the links of what these relations actually are. If you run a dependency parser, it might be a good idea to take the parent node word of the current word. It's a perfectly reasonable thing to do, and people will do that. So when you do things like this, you quickly discover you're getting classes of things, but also when you look at the pointwise mutual information, see we haven't even got the positive thing in there because we've already got it, because it's always going to be positive. Instead of the counts, what you quickly discover is that, what are the objects of drink, and they are things like tea, liquid, wine, anything, and it. Wait, what? It? Because it might say drink it, okay? And it appears often, but it's not really something you drink, because it also appears in other places, okay? And so one of the advantages of actually trying to use pointwise mutual information is you end up with a much higher score for things like tea, because tea is more likely to appear with drink than anything at random. Well, it appears with lots of things, okay? And this is also the case when you look at things that tell you automatically try to discover colors. I remember somebody showing you this, that one of the most common colors that you actually get in things is called other. Because often it says, this is available in red, blue, or other. Okay? And other is a very common color. Okay? No, it's not. It's a sort of generic other color, but other appears as a color, but it isn't. Okay? And so this is a good way to be able to find out interesting properties about particular objects without us knowing it. So this would work with other languages as well. Claire?
If during your pre-processing step, you replace all of the its and the others with invalid tokens, would the dependency parser break?
No, the dependency parser probably wouldn't break. It would give you something else. And you would still have your other token being there.
But then you do like...
If you could do an alpha resolution and replace it with the thing that was being talked about, then things would be wonderful. Okay? But we all know that that's hard. But this might be an easier way to get the same result. And really what's going on here is that it appears in lots of different places as well as drink. Well, tea only appears in drink or dumping in Boston Harbor. Okay? So there's limited places that go, well, it is really pretty generic. Okay? Which brings us to this other thing that I know some of you have found, a thing called TF-IDF, okay? Which is term frequency inverse document frequency. And what this is trying to capture is that thing that I mentioned about T. T will most often appear as the object of a verb that's got something to do with drinking, buying, selling, appreciating, because it's some type of drink, okay? Well, it appears all over the place, okay, and it's much harder to classify. And so what you'd really like to know is a sort of score for a word of how likely this is going to appear in this document and not other documents. When I say documents, it might mean sentence, but documents, okay? And so what you'd really like to know is, for this document, over all my documents, which thing is the most unexpected distribution of the word? So if this is an article about, from Wikipedia, you would expect that tea is much more likely to be in articles about tea, okay, and the tea plant, okay, and the British Empire, because the British Empire's sole purpose was to provide tea to people in England. That's only partly a joke. It might actually be, it was a very important part of the British Empire, so you'll find tea being mentioned there, okay, and the reason that the people in Boston got rid of the tea was not just because it was a tax, because it represented the British Empire. And this is why I can't get cups of tea in this country, because you banned it, 250 years ago. Okay, I appreciate all the Asians who are here at CMU, so I now can get real tea. But anyway, enough of the complaint about the British Empire. And this is talking about, of the particular document, you'd expect tea to appear a lot in there, and not to appear in the article about Nebuchadnezzar. Okay, because he didn't care about tea; he wasn't part of the British Empire. Okay, so which words are less likely to appear in this article compared to other articles of the distribution overall? So things like the appear everywhere, so it's almost useless a way to identify anything. Same with it, but key content words can actually be very useful in a way of identifying what the document. And if you look at the words in a document that have the highest score, they're usually the important words that are in the article. Okay. And so what we're doing is we're basically looking at the term frequency, okay, what's the likelihood of this particular word, Nebuchadnezzar, okay, and what's the inverse document frequency with respect to this particular document, is it appearing more often, okay, compared to others. TF-IDF is usually done for longer things, at least sentences or paragraphs or maybe documents, because you sort of have to have enough data in the thing that you're comparing, because each sentence has got maybe not got overlap of words, and therefore it can be harder to do it. So there's often very unique words in a sentence, but if you go to a paragraph or you go to multiple paragraphs, a whole article, it's much easier to know which of the important ones of the document is. Looking at the single sentence is not as reasonable to do that. Okay? But so far, what we've been doing is, for our vectors, is we've mostly been caring about sparse vectors. So we've got some set of words in our vocabulary, and we're going to have either a PPMI value or 0, okay, when it's a low value, in a big vector based on the vocabulary that we're dealing with. And we know our vocabularies could be very big. Even if we do targeted vocabularies for a domain, get rid of the really high frequency words and just use the ones that are interesting, it's probably going to be thousands or maybe even tens of thousands wide. And there are good representations for that, and there are good ways to be able to manipulate them, and good libraries that help us do that. But we have a very wide vector where many of the things are actually 0. And the question is, could we try to reduce that into a more dense form so that it would be easier to process? Okay. We'd like things to be shorter. If we can do it, we like them to be dense so that we're not wasting zeros, we're not wasting space, so that we can actually try to get something that's more compact of the information that we'd like to deal with. Okay. Short vectors are quicker to train from. Okay, and if they've got the dimensions we want, that's going to be better. And you might think, computers are fast, that's not a problem. Yeah, but it really is. If you're training on all of Wikipedia and every single word is going to have a representation that's 20,000 floating points long, it takes a long time to process. Okay, and so we'd like that to be orders of magnitude faster. Okay, dense vectors may generalize better, and they might be slightly better at getting synonyms, and actually it turns out that they are, but that was post hoc and discovered, not actually something we'd like to do. Now, what we can do is there's 3 potential ways of trying to get so-called dense vectors where we're trying to get them reduced. One is we can do math on our sparse vectors to try to reduce them. Okay. Things like singular value decomposition, or PCA, allows us to be able to look at the average of them and try to represent that and look at components of what's in that form and try to look at the most important components. That's almost for looking at what's the most important words over all of the data that I should really keep the values for and get rid of the ones that don't really make any difference whatsoever, because we've got this column with Nebuchadnezzar that never gets used, okay? And so we could get rid of that. There's a way to sort of try and automatically find out about that. We could use neural language model techniques to be able to do this, and we're going to talk a bit about that. And that's the way that we mostly do that nowadays. So we actually say, I'm going to get a representation, and we're going to use a neural net to be able to predict what these numbers are. However, there's lots of experiments that show that actually what it's trying to do is approximate the first value. It's actually trying to approximate the function that's on the first line. Okay? Or we can use Brown clustering that's interestingly different. Okay? So we'll talk about that later. Okay? So let's talk about the automatic math-based reduction, okay, the analytic reduction, rather than the neural autoencoder reduction, okay. So what we can do is we've got this n-dimensional space, we can try to rotate it across different axes, and we can try to find ways to be able to reduce it. And there's a bunch of cool math from stats, which is already there, that will do that, and people have been doing this for hundreds of years. Actually, I don't know if it's hundreds of years, but at least longer than since I was an undergraduate, which might have been hundreds of years. Principal component analysis is one of the most common ones that would allow us to be able to try to find the most important axes that's actually in the data. Factor analysis allows us to be able to try to separate these out, and singular value decomposition is another way of trying to reduce the dimensionality of the data by looking at its distribution. What you're really doing is you've got this n-dimensional space and you're trying to find the one that's got the biggest variance in it, that tells you the most about the prediction, and what you're going to do is I'm going to keep that one, okay, and I'm going to subtract that mean dimension from everything else, and I'm going to look at the next most predictable one. And so what you end up with is, when you have this big long vector to begin with, the thing that you get out of it is you're going to get an ordered vector where the things towards the left-hand side, if there is a left-hand side of a Python array, are the things that are more important, that have got more predictive power than the things at the right-hand side. And then you could say, I'm going to take the first n, okay? And this allows you to get a compact representation that allows you to get the distinctions out of this. Okay. Let's talk about. Sorry, I can't remember, and I can't see the thing on the screen, so I have to read what's going on here. It's just the math. That's just math. That's just math of reducing it. Yes, this is what I wanted to talk about. So there are standard techniques that allow us to be able to reduce it, but how much do you reduce it to? And realistically, you reduce it to the thing that still allows you to do whatever you want to do. Okay? So there's no absolute number for this. It seems, at least for the last 10 years, we think it's 300. Okay? But I'm pretty sure that the first person who was doing this stuff in natural language processing said, I don't know, 300. Okay, and you can do tests, and people do, 100, 200, 300, although it probably should be 330, 300, 3000, because it's probably logarithmic. But, for a long time we seem to use the number 300, and it's not exactly clear why. Okay, it does work, okay, and sometimes you want to make it smaller because you don't have enough space and you've got more data, and so you can actually do it. It's probably fundamentally got to do with what's the distribution of words and distinctions in the data that you have, which you're not going to know the answer for. But if you were in a data set where it's smaller with much more distinct words in it, let's say reviews of restaurants, so you're in the restaurant domain, 300 might be too big. If you're in Wikipedia, which sort of is supposed to be anything, although I think the news domain is bigger because it talks about individuals while mostly Wikipedia only talks about famous individuals. Even though there's more data in Wikipedia, news is probably a harder domain. You might want it to be bigger, but most people use 300, but I'll come back to that. You can weight things as well, and there are different ways of doing that, but again, based on the particular form that you're doing, you can do that in different ways. I'm skipping the math here. So dense vectors, however you get them, can often have good properties about when you're training. If you make them dense, they can be much more robust, because you're getting rid of probably tens of thousands of lower order forms that will have random noise in them, and you're just getting rid of them. And so often they're more robust. You can use them and be more reliable that the distance metric you get isn't sometimes stupid, but sometimes you get, okay? And for accidental reasons of distributional properties. The truncation gives you generalization as well. So it actually forces things to care about the most common general forms that have good distinctions in them. And therefore, this is typically good when you're dealing with new data that you've never seen before and you get generalization. So it's a good thing to do in general. Smaller number of dimensions makes classifiers actually more robust because you've only got the most predictable or the things that are more important by some definition of important. And so in general, it's a good idea to do this. If you've got an awful lot of data, making it longer can be a good thing. And now in some of the later things that I'm going to talk about, it might be interesting to do that because you could try to capture different aspects of dimensionality. But here, 300 is probably fine. In fact, 100 for many of our tasks is probably fine. So people knew about doing SVD on vectors with PPMI for some time. They're quite computational and expensive to do. They're usually trained on a particular data set that you're dealing with rather than having pre-trained data from somewhere else and then copying these across, because that usually didn't work. And people noticed that in neural nets, they thought, well, actually, maybe we could train these things and maybe we could get a better representation, okay, that actually is more appropriate for our particular data set. And so people started looking at this, and we're going to talk about two particular here that are now relatively old, they're like 5 or 6 years old, skipgrams and continuous bag of words, CBOW. Okay. Skipgram was 2013 from Google, Mikolov, continuous bag of words was a slightly later thing. They're somewhat related to each other. They're sort of using the same architecture to do something different. Basically, the fundamental idea is, if I look at the context of the words I'm in, can I predict the missing word? So if I've got this word, okay, and I look at the context, can I predict what that word is? Okay, so what I do is I look at a whole bunch of contexts and take out that word and try to find out if I can predict what that word actually is. Okay, now sometimes that's really easy. Okay, so we can say President Donald J. Blank came to Pittsburgh yesterday. Okay, and what word do you think that is? Well, there's lots of context. Either you actually know the fact that he was here yesterday, or you know the fact that Donald J for president is there's only been one Donald J. I actually don't know if that's true, but at least recently there's only been one. And so you can predict that as Trump. But there are other ones that are just incredibly hard, okay? So if you have something like, there are milliliters in the bottle, I don't know what the number could be. It's probably not going to be 10 to the 18, but it's probably going to be something between 1 and a few hundred, 1,000, I don't know. But you have some constraint what's actually on there. But if you look over a whole bunch of data, you could try to find out how well can I get a representation for a word given its context. Okay? And this works surprisingly well. So you're predicting it would say 2 words before and after. So you've got 4 words that you're trying to predict what the current word is. And this is what skip grams are trying to do. Okay? And so you're looking again at context of what's actually there, but instead of explicitly doing it with respect to these sparse forms, you're actually doing it using neural nets, and you're doing it in a constrained form, and the representation must allow you to reconstruct the word that's actually missing. Okay, I'm going to skip these. So what we're doing is we have some representation of the word. We'd like to get the projection, the reduced form, and we have to be able to predict the context, or reverse, we've got the context and we're trying to predict the word, but we're trying to make that prediction, the representation of the information, will be 300 vectors, 300 floating point numbers rather than 10,000 as it might be out here. Okay. When you predict the information, you get a one-hot vector of what the word actually is. So we're still predicting to a sparse representation, so we know what this dense representation actually represents, and there's a neural net that does the decoding to tell you which word it is. You can also get it to give you the probability, or the probability of the words that are actually appearing in there. But we've maybe got, in the Mikolov case, 300 numbers that actually represent it. How do we learn these neural nets? I'm not going to go into the details of that. You can read this. Okay. The continuous bag of words is still a similar architecture, but what we're doing is we're predicting that layer from its context, and it gives us clusters that are things that are close to each other in the embedded space. So we just do Euclidean distance in the embedded space, and we find out what are the most common things that go together. And what we find is that Redmond goes to Redmond, Washington, Redmond, full Washington, and of course Microsoft, because there isn't any other company than Redmond, Washington, apart from Microsoft. That's actually completely false, especially now, as Facebook, Google, and Amazon all have places in Redmond, although Amazon's really downtown. If you get Havel, other close by things are Václav Havel, President Václav Havel, the Velvet Revolution. Václav Havel was the first president after the fall of the Eastern Europe in Mumble country. That's a little embarrassing. Which country was it? Hungary? Okay, we should know that. That's embarrassing. I'm glad we're not recording OBI with while ninjutsu matches to ninja, martial arts, and swordsmanship, graffiti goes to spray paint, graffiti taggers, and capitulate goes to various morphological variants of those. So things which are close together are actually discovered automatically from the form to be able to do them. Okay. Now, there's actually an interesting thing that Mikolov noticed. Oh, sorry, it's you've been drinking some of that whiskey we were mentioning earlier, and it looks fine to me. But look at the graph underneath. There's something interesting about these representations that Mikolov noted, and nobody's really quite sure about this, although lots of people hypothesize. But let me explain what it is. If you have a representation in this 300 floating point, and it's a representation, and you can do arithmetic on it, you can do subtraction and addition, okay? And what it appears that if you take the representation for king, okay, and you remove the representation for man from it, and you add the representation for woman to it, you get close to the representation of queen. Ooh. Wait, are we getting decomposition of the representation of semantic features in words in this 300 floating point representation? And the answer is sort of. Okay? It breaks down when you start trying to look at specific things that you know should be there, but for some gross high-level things, especially things that are very pertinent to the particular word, like especially king and queen, one of the properties of king is that it's male, it's very important that it's male. Well, if we take something else where it's not as important, doctor. Yeah, people probably think of a male doctor. If you type doctor into Google Images, you're going to get pictures of male doctors before you get pictures of female doctors. But doctor is not really gendered. But king and queen are really very strongly gendered, and people are very much aware of it. And so we find that we get some notion of information like this. Also, you find that we can get singulars to plurals this way, and so this is sort of interesting. There's some more meaning in the vector than just quite simply a simple distance vector. There's some factorization information about the dimensionality. Okay. Everybody to begin with was training their own vectors to be able to do this, because it was really important to get them for their domain. But Google, who have all the data on the planet, said, well, maybe you could pre-train this. So what I could do is I could just go and take all the data on the planet, or at least something very big, and train a bunch of vectors for it. And if you want to use a vector, instead of you having to train your vector on all of your data, which could be computationally really expensive, what we'll do is we'll just give you a library that you can look up, and you can get your 300 floating-point numbers that represent king and queen, etc. Okay? So they did that. And the Miklos stuff is under a system called Word2Vec. You can train that yourself, okay? Or you can just use the default information that comes from the nice, cute Python library that's there. Now, you might ask for a word that Google doesn't know about, okay? And it will give you the unknown word representation, okay? So you can still deal with that, but it will work, okay? And it's worth considering. So for example, if you were doing a homework and question answering on Wikipedia things, it might be reasonable to consider to use word embeddings from Word2Vec. There's another very common one called glove, which everybody thinks is just a comparison neural net form, but glove is not. Glove is actually, like the earlier thing that we were talking about, is derived from data rather than from a neural net. Okay? So they do positive piecewise mutual information, and they do a data reduction form. I can't quite remember if it's SVD, but something like it, and they get a representation. And sometimes glove is better. It sort of depends on the type of data. And so it depends on the type of data that they trained on. And it probably also depends on how general your use of the language is. So for example, if you're doing Wikipedia, and I think both of these used Wikipedia as part of their training, so the type of language that's in Wikipedia is very didactic, very explanation-like. It's got strong editors who correct things and stop using really obscure words. So it has a certain style that's in it. If you use these for, say, Twitter, it would suck, okay? Because the words in Twitter are, one, got a very different distribution, okay? The first person singular I appears in Twitter all the time, but it's relatively rare in Wikipedia, okay? At least if you look at the distribution of the words, okay? But there's more, okay? Last November, another group at Google actually said, well, you know, we've got a representation of the word. What happens, we're ignoring the actual context that that word appeared in, okay? So maybe we should do something more about that. One, explicitly for things like the word apple, which could be a fruit, or it could be a computer, or it could be a computer company, okay? But also we should maybe just have a different representation of a word depending on the context that it's in. So we can actually try to learn that. And so a bunch of people at Google last year put together a system called BERT, which actually tried to do that. There was an earlier thing 6 months before called Elmo. For those of you who are not American, these are both characters from Sesame Street. I'm not American, so I wasn't really aware of what all these different characters are, but they're Muppets, funny puppet characters. And Elmo did just before, which was the first one to care about context. But BERT came out in November, and appeared at Archive and provided a tool that allowed you to give it sentences, not words, sentences, and then you would get the word embeddings for each of the words in the sentence. But you have to give the whole sentence, not the isolated word. Okay? And so it's slightly more computational to do. It certainly has to do computation at the time. It's not a big lookup table. Google doesn't have a big little lookup table for all possible sentences that we've done. Okay? Just taking my time. And BERT came out in November. 3 weeks later, there was a deadline for North American ACL, which is one of the major NLP conferences. And I didn't go to North American ACL this year, but I asked one of my students who did go what they thought the most important thing at the conference was. And they said, things are better with BERT. And they said most of the papers at the conference, not all, but most of the papers at the conference was like, I used BERT, my thing got better. Question answering, summarization, storytelling, everything got better. And BERT is one of these few things that's happened in natural language processing where, in general, everything gets better if you use the embeddings for BERT. Okay? There are circumstances where it will not get better. And again, if you have words and syntax that are used in a non-standard way, that was not what BERT was trained on, it's not going to work. You could train BERT, but it's computationally really expensive. Google trained it over periods of 2 weeks on their machines, and they've got more GPUs than you do. Somebody calculated, it's in a paper here that came out as a competitor to BERT. They calculated that CMU could actually do the BERT full training in about 2 weeks as well. But that meant using every GPU on campus, okay? Which I'm not giving up my GPUs for that because I've got my own deadline to do that. But BERT came out in the beginning of November, and 3 weeks later there was a conference deadline, and many papers ended up using it, and everything got better. So that's a little hint to you if you're thinking about using embeddings for things, especially if you're in a domain where BERT's quite good at, like Wikipedia. So it's something to consider. It's computationally a little expensive, so that's something you maybe could, and maybe Word2Vec is good enough for what you're doing in Wikipedia, but it's something to certainly consider. Now, here's a little word of warning though about BERT, is that BERT came out, everything was wonderful, everybody made these things better, almost all computational things with neural representations got better with BERT, and of course everybody's trying to come up with better representations. So since BERT's come out, there's been at least 3 things I can name, but probably more, that are better than BERT. In fact, if you read the BERT paper, it says there are many ways to do this, and there are many things we're not considering when we're looking at contexts that we maybe should, and maybe they would give better results, but we've not investigated them. One of the more recent ones that I've got to talk about is XLNet, which was developed here at CMU by some students in language technologies, and they also get something that, for a whole bunch of tasks, it's better than BERT. Okay, and it's just changing the way that people are actually doing the training, but they end up with something that's better. They don't quite have such a good interface to make it easy to use, but you could use XLNet as well, or you could use BERT. Okay, and there are other modifications of BERT, usually with the name BERT in them, like Albert or Roberto, that are doing very similar things. But I'd just like to say that this field is moving incredibly fast at the moment, such that during this lecture, there are probably new things on Archive that are better. Okay? Better than the previous ones, and the other ones are better than BERT, but if you want to pick something at the moment, BERT might be a good thing to consider. And we've hung here, but we've not hung here, so it's okay. Brown clustering. Okay, I said this one's different. This is actually relatively old, and it's for years I used to think it was based on what was called the Brown corpus, which was a corpus of data from the 1960s, taken from different genres, including magazines, books, etc. But no, it's from Peter Brown, who was a researcher at IBM and primarily was doing this for translation. And what he wanted to do was he wanted to find similar classes of words, a bit like part of speech tags, but something that's closer to the concept of, like we looked at the beginning, of looking at the context of the word to try to find out its a little bit more semantic meaning. Okay, it's the agglomerative clustering algorithm. And so what we're doing is we're going to say we have all the words in the data set that you're training from. You have to do it for a particular data set, all the words. And what you're going to do is you're going to try and find the distance in the context space for all of these words. And the ones that are closest together, you're going to join together. Okay? So you're going to look through all this stuff, and eventually you're going to discover that red and blue appear in almost the same context for the whole data, and so we're going to put red and blue together. Okay? And then we're going to look at red and blue as a new class, and we're going to look at everything else, and we're going to try and join them together. Again, this is computationally expensive, but can be parallelized pretty easily. There's good GitHub code that I've used that worked better than my original implementation I didn't use. But we're just going to talk about it because it's actually often quite a common thing to do. We do it still in translation because especially it can be targeted to the particular domain much easier. Okay, so to begin with, we've got every word in its own cluster. And what we're going to do is we're going to look at the context for all of these words through the whole of the data set. And then what we're going to do is do some distance metrics in the word space, not embedding space, although that would be interesting now to do that, to look at which contexts are most similar over the words, with some little bit of normalization to make sure that we deal with the fact that there's going to be different distributional information. Okay? So you end up with a tree, okay, as a representation where at the furthest down you'll find the most similar things, and as you move further up you're going to get these clusters that are going to, until you get a single cluster at the top with all the words that actually appear in it. So you might get something that the chairman and president are somewhat similar, the months are similar, run and sprint are similar, but not very far away from walk. Okay? It's always binary branching, okay? And so what you can do is you can label all of the nodes in the tree with a 0 or a 1, so if it's the left-hand node it's a 0, the next one is a 1, and then for each word what you can do is you can read off a binary number by going down the tree to get a representation. The binary number, the distance between it and the binary space, is going to tell you something about the distance metric between them, okay? Because the lower bit numbers will mean that they were in a similar cluster, okay? And this works surprisingly well, okay, especially on not general domains, because it's sort of too computationally hard to do over Wikipedia, but if you have some particular data set, it can give you interesting clusters that can help you do interpretation, help you do translation, help you find out when words are actually similar, that would allow you to be able to flip between them. And so the brown cluster examples, if we do it on, I don't know which data set, Friday, Monday, Thursday, Wednesday, Tuesday, so days of the week, but also weekends, okay, and notice that we're also getting plurals as well, singulars there. We get months, okay, and we get pressure, temperature, permeability, density, porosity, all things that might be some form of measurement, okay, and we get anyone, someone, anybody, somebody. We get a bunch of modals, we get a bunch of things that people might do when they're considering a statement, asking, telling, wondering, instructing, informing. We get family relationships, and this is all completely unsupervised, okay, based on the data, okay? So you're finding these words as being similar in brown clustering without actually knowing anything about the data. And we've done this on languages I don't know, and then you go and ask some native speaker and they go, yeah, that's family relationships, that's colours, that's food that everybody enjoys and makes you sick, that's food that everybody hates but makes you healthy, okay? And so you see that there's nice relationships between that. It's not clear what these relationships really are, always, because these are obvious ones, but as you go further down you go, yeah, well, maybe, I suppose. But they're derived from the data, and they often help in things like translation or simplifying things in language modeling. Remember, one of the reasons that we do part of speech tagging is to be able to reduce the number of tokens that we're dealing with when we're looking at sequences, and this will allow you to reduce the number of tokens to allow you to look at sequences and make predictions and get better models. But Brown clustering is sort of a different way of giving you some limited form of representation where a distance metric means something, again though, based on the environment that it's in. All of these things that I've talked about today is trying to get a representation which is all fundamentally based on the environment that the words appear in. Okay? And that's what we're taking as being meaning. It might not be meaning, but it's typically useful for many of our NLP techniques that we're actually doing. Okay? Here's math. Yeah, okay, so how do we know it actually works? Because we get this bunch of random floating point numbers. Well, there's various things we can do. People have used it for question answering, which would be important, or spelling checking. One of the things that we were recently doing with Bert was basically saying, we look at the sentence and we find the unusual word in the sentence, which is probably a spelling error, and we say, what's the most likely other word that should be there given the context? And that's usually the spelling, the corrected form of the word. So it's a way to take out a word and put in another one that's probably the corrected spelling. You have to be a little bit careful about that, because it might also be just really high frequency things. So if you have a sentence that says, ice cream is awful, it might get rid of the word awful and replace it with yummy, because that's the more likely thing that people are actually going to do, but maybe not. SE grading, there's a whole bunch of these interesting things. You could try to actually look at the distribution itself and start to look at distance metrics between it and things that it thinks are similar or not. And Julia Svetkov, who's a professor in language technologies, she teaches 11711 algorithms for NLP. Her thesis was about trying to look at how do you measure how good word embeddings actually are, so you can actually evaluate their quality. Downstream tasks are a very reliable and useful way of doing it, but can you actually do something a little bit more abstract than that? And there's stuff in the thesis about that. So what we talked about today was distributional vector models of meaning. So we're trying to get a bunch of floating point numbers to represent the word rather than just the word. Okay. We're appealing to the idea of looking at the context of where that word is and representing it with respect to the other words that appear round about it when that word gets used. We talked about the sparse representations where we've got all these other words that could appear and we have a value about how much it appeared. In some sense it could just be its actual frequency, but it could be positive piecewise mutual information. Then we talked about how to do this dense representation, and we talked about 3 particular ways of doing it. We could actually do it with some sort of dimensionality reduction form, latent semantic analysis, etc. We could do it with some sort of train from data, like skipgrams or BERT, if we want to care about the contextual form, or we could do it with some form of Brown clustering or something similar to that. All of those will allow us to be able to get a denser representation that would allow us to get a distance metric that would tell us something more useful about the words. Okay? And that's it for today. I'll just say a final thing about the exam. You got a mid-semester grade if you did the exam. If you did not do the exam by last Thursday, because we've not graded all of them, you just didn't get a mid-semester grade. We will give you a mid-semester grade, but it won't appear in the system because we don't have a time machine to take your grading and then go back in time and give you one. If we did, we would do that. Okay? So if you didn't do the exam, but you've now done it since, and you're going to do it, there's another session tomorrow, you will get a mid-semester grade and be told about it, but it won't be officially in the system. Okay? And once we've got graded everything, we'll give you stats on the whole exam, telling you what the range of grades are and what the distribution actually is. Okay? Thank you.